What speed does Ethernet run at? Well, the latest speeds are 40G and 100G. 10, 100 and 1 gigabit versions up until that point, up until 1 gigabit, people said that Ethernet means CSMA-CD. So those standards have CSMA-CD versions. Even though they are not used, but the standard spent half of their pages describing CSMA-CD. After 1 gigabit, they said, forget CSMA-CD. We don't use it. Why waste time on this? 10 gigabit standard has no CSMA-CD version. Obviously, 40 and 100 gigabit do not have any CSMA-CD in it. And even at 10, 100 and 1 gigabit, nobody uses CSMA-CD. Even when you go buy a home $5 switch, it doesn't use CSMA-CD. Okay? Everything basically is full duplex, and then basically that means there's no collision. 1 gigabit today we use in home. If you buy a switch today, everybody buys 1 gigabit. I mean, you can get for home purposes a 5 or 8 port switch for $20, $30. So you don't even care for getting 100 megabit anymore. 100 megabit will be much less, maybe $5, $10. In enterprise offices, like this WashU is an enterprise. In the offices, we use 1 gigabit. 1 gigabit is in the data centers, but moving to 10 and 40. 100G is in some core network, carrier core networks. What is a carrier? Carrier is companies like AT&T and Verizon who transport long distances. They might be using 100, but the problem with the 100 is that it is still more than 10 times 10 in price. And that is what people don't like. See, the thing is, everything about the Ethernet was that every time we went up the speed, we made sure that the price didn't go up by the same number. You go up in speed by 10, price goes up by a factor of 2. So for twice the price, you can get 10 times the speed. So that's why people move to higher speed. But that is not happening with Ethernet. 100 gigabit Ethernet. It is not price competitive at this point. So if you want 100 gigabit, how do you do it? You just buy 10 gigabits. That is cheaper. Okay? And you get 100 gigabit. Now, there is one interesting note I want to point out. People don't understand that we always, networking guys, we talk about bits, not bytes, first of all. Okay? Second thing, we talk in decimals, not in hexas or binary numbers. And so when we say 10 gigabit, we really mean 10 raised to 9 bits per second, period. Okay? And why bits, not bytes? First of all, the days when we started networking, and I remember having a modem which was running at 110 bits per second. 110 bits per second, period. That's it. Not 1000, not mega. So in those days, if 110 bits per second somebody was selling you and said this is divided by 8 is 12 bytes per second, would you buy anything? No. So 110 sounded much better number. So we started with bits and we are still at bits even though we are in gigas. Storage is a different story. I mean, obviously we don't deal with bits in storage, we need bytes, and in networking we need bytes also. We never transmit bits alone. So in storage, they started in binary. So they said 1K is 2 raised to 10, not 1000. 1K is 2 raised to 10. So that is 1K. 1 meg is 2 raised to 20. That's not same number, right? And 1 gig is 2 raised to 30. So when you buy, so now they are cheating you. How they cheating you? Is that you buy a disk and it will say it is a 256 gigabyte disk. So you would think that it is 256 times 2 raised to 30? No, it is 256 times 10 raised to 9 bytes. And then when you put it on the computer, it will show you that you have a 238.4 gigabyte disk. Because the computer really needs 2 raised to power something. Okay? That's how the disk capacity goes down the minute you put it into your computer. Because the seller is selling you in the decimals, but the computer is expecting it in binary. You understand the difference? And they always talk about in bytes. We never talk about in bytes. We always talk about in bits. Moving on. So if you want to get 100 gigabit, I told you that the best way to get 100 gigabit is to buy 10 gigabit links. But would they be treated like 100 gigabit? The answer is yes. There is a standard called Link Aggregation Control Protocol, LACP, which allows you to take any number of links and make them look like one link. Alright, that standard is called 802.1ax. Now here is the interesting thing. We are talking Ethernet, but this is 1ax. What that means is that these links don't have to be Ethernet. If you take 10 Wi-Fi links, you can combine them into one. You can take 10 WiMAX links, combine them into one. Previous to this, there was an old standard which was called 802.3ad. That was for Ethernet. That's how it started. Okay? So the Ethernet started the link aggregation, but now it is whole 802 wide. And so basically you can take 3 1 gigabit links and make them as one 3 gigabit link. You can form any link speed, and the advantage of doing this is that it allows some fault tolerance. If one of the port went bad or one of the link got cut, you still have the rest working. And obviously you have this capacity increase. If you need 3 gigabit and or you need 100 gigabit, there is sometimes it's not possible to get that speed in one link anyway. So you do multiple links. Now there are several extensions to this. For example, some companies allow you to aggregate the links to 2 switches. For example, you could have a link, this one and that one, and these 2 switches will somehow combine to look like one switch, and then you have a 2 gigabit link. Alright, how the switches combine, that we'll talk about when we do virtualization. But basically you could have the links going to virtual switches and they are aggregated. So spanning trees again taught in 473, and basically the idea was if you have an Ethernet like this, and if you send a broadcast, it will go from here to there, from there to here, and then it will go there and then come back. So it will be circulating in the loop forever. How do you get it out? You cannot get it out. So basically the idea is we want to break all the loops to make a tree. So instead of this, we break this link and we break all these links here as shown in dotted line. Now we have a tree from the same configuration, and now if anybody sends a broadcast, it will not come back because there is no loop. Right, so this is the spanning tree. And the way a spanning tree works is that it has a root, and so anybody who wants to send to anything else knows only one direction. So if it wants to send to any of these guys, it knows, well, I have only this link. Now if it wants to send something, it sees whether it is to send here or here or here, 3 links. So it just remembers that all the destinations, these destinations are on this link, these destinations are on this link, and so on and so forth. So for every node, there is only one way to go. You keep a table of MAC addresses, and there is only one way to go. Generally, you go to the root and then come down. And so basically, this is the spanning tree. Now, how do you find the root? The way you find the root is that the bridge with the lowest MAC address is the root. Is the lowest bridge address. If there are multiple, if you want some, and 2 things you take. You take their root priority, so you give everybody a priority. I have the highest priority, I have the lowest priority. The lower is better. So I have, let's say, priority 0 and you have priority 1. So they will first see, is there anybody priority 0? If I am there, then they will say, okay, what is your MAC address? What is your MAC address? You are also 0. Whoever is the lowest in the priority as well as in the address will become the root. Alright, and so you just tell your neighbor what is your priority, what is your address, and they tell to their neighbors, and they tell to their neighbors. Everybody says, and then finally we'll figure out who has the lowest. Basically, spanning tree, what it does is it makes a tree out of any graph. You can connect the way any way you want, and the computers or the switches will automatically figure out which links should be disconnected to make it a tree. And the way it works is that they select a root, and root is the one which has the lowest priority and the lowest, so it's not really called priority because priority means, just the opposite. So which has the lowest priority and the lowest MAC address in that priority. So every bridge, every switch is administratively assigned a priority. So the manager sets the priority into the bridge, that your priority for beginning the root is such and such, or it might be default be 0. If you don't set anything, then everybody is at the same priority. And then every bridge, every port has a MAC address. And therefore, we can figure out who has the lowest ID. So taking the 648-bit MAC address and 16-bit priority makes the 64-bit ID. So everybody advertises to the neighbors that, look, my ID is so much and I am the root. then you advertise, basically first you check it out. It is quite possible that you have a lower ID, so you could say, no, my ID is this much and I am the root. So whoever hears from a higher ID stops. At least they stop saying the root, they start saying the other guy is the root. So they might say, well, my ID is such, but I know that this ID is the root. Alright, you tell your neighbors and their neighbors and their neighbors. The whole network knows who is the root. After they know that the root has been selected and everybody knows that this is the root, they try to figure out what is the shortest path to that root, and that is the link that is active, and any link that is not on the shortest path is basically to the root is not active. Well, so the activity is on both sides. For example, if this one declares this to be active, then this obviously will be active from this side, from this node. So basically, with that method, so here, for example, this link is not the shortest path to the root for this node and not for this node either. So this link will be blocked, right? And so at the end you will get a tree. And then when the packets have to be sent, they have to follow the tree. If you want to send from here to there, it will go all the way to the root and then come down. Even though there is a link here, but it is blocked. If you want to go from the leftmost to the next one, you just go up to here and come down. So the good thing about this is that everybody can come in only from one port. So for example, this port will be seen by this host only on this port here, on the top port, because this to come from here you will have to go all the way here and come here, right? You cannot go from here, you cannot go from there or any other place. So there is only one input for each, actually not just for the bridge, for each node in the network. And that way we can learn where you are. So basically that's how the Ethernet learns where you are, is it just monitors all the incoming traffic. Whichever door you come in, that's the way you are located, that's the way we will send the packet out to you. Understand the source learning algorithm? Right? Some of you probably have learned this before. Source learning. And the bridge minimum cost to the root becomes the designated bridge. Yeah, so basically from here you will send it to this. Actually, designated bridge will become more clearer on the next slide. So just hold on to that thought for a minute. All ports of non-designated bridges. So some bridges, actually when you have here in the previous picture I did not show you the real Ethernet because everything was just like point to point. In the real Ethernet you might have many bridges connected to the same wire. By the way, we don't use it anymore. But in the original Ethernet, this is where we use CSMA CD, everybody was connected to a wire. There used to be a wire going into the roof, or not roof, ceiling, and people would just go and clamp their computer there. These are all switches here. These are all bridges here. I haven't shown the host. Host might be hanging off too from the same wire. This is old in that sense, right? But just for the sake of that. So here what happens is that there are many bridges, and these are the MAC addresses I have put there just arbitrarily. They cannot be so simple, but I have just assumed that these are the IDs now, and all of them the same priority. In this network, what would be the route selected? So this is the network actually in the beginning, and then so 101 will become the root. So this is shown again the same thing, that 101 is the root. Now 101 is the root, and so basically on this Ethernet 101 will be the designated bridge. On this Ethernet 101 will be the designated bridge. On this Ethernet 107 will be the designated bridge. Right? Because it is closest to the root. And the closest means distance in number of hops. Right? Because right now they're all same speed as well. If they were different speed, then the closeness will change. But right now this is one hop from the root. So this is 107 is the designated bridge. These two are not. If there is another host here that sends a packet, wants to send a packet, and for some reason it has to go through the root, then it will go to this bridge, right? So basically all the packets will be forwarded on this bridge by this host, by this bridge, on this Ethernet by this bridge. That is the designated bridge. Because if they go through the other bridge, they're going in the wrong direction. So that is the designated bridge concept, is that there could be many bridges on the same Ethernet, and if there are many, then one which is closest to the root will become. In the previous picture, there was not such a case because every link was point to point, and so we did not show you the multi-point links. It becomes clearer here. Bottom Ethernet, what would be the designated bridge? Now there are two of them, right, which are equally close, which are equally close. 102 and 104. 105 is not connected even because it is blocked. You see why this is blocked? That's the one thing I wanted to explain, but let me just first. So what will happen is here there is a tie as to who can be the designated bridge, and generally tie is broken in favor of the lowest one. So 102 will become the designated bridge. Now let's see which link will be blocked here. So let's just go through this. First of all, it is very easy. Just by looking at it, you can figure out that 101 is the root. Right? I mean, of course, there is an algorithm and broadcast and everything else. We can go through that process, but at the end, it will come out, if everything is done correctly, that 101 is the root. The next thing they do is, everybody figures out, am I connected to the root? And which way I can reach the root, right? So this one will figure out that I can get to the root from here, 105, if we figure it out from here. And so it will disconnect, and there is nobody else who will want to reach from here. Everybody else has a shorter path to the root, and this will get disconnected. This will say, I'm going to disconnect it if nobody else wants it. And since nobody else wants it, 106 can get to 107, and 103, and so on and so forth. Everybody has a path to the root. So this link will get disconnected, and I think this whole Ethernet will get disconnected in that sense, is that, if there was another bridge. So right now what is going to happen is everybody is hanging off, just one hop away from the root. These are 2 hops away from the root. There is no human intervention required, because these links will be coming up and down. If some power fails or something happens, the link may go down, right? So we don't call the human being to come and fix it. The network takes care of it, right? This link may come up if for some reason this Ethernet goes down, or this Ethernet goes down, then this blocked link will come up. Okay, so that is for all data traffic. There are 2 kinds of traffic, data and control. Data is what I and you send. Control is what the switches send to each other for keeping the thing alive. So there might be some hello messages that might be being sent that, okay, I'm connected here, I'm connected there, are you still there, is the root still there, is the root gone? All those control messages, probably some of them will be exchanged here, so that they know that the link is there. Link is there, they know, but they're not sending any data on it. Or they just exchange the control traffic. So this one will say, I have a short path to the root. The root is 101, and you can reach it to me through at cost 1. Right? And this one will say, I have a root 101, and you can reach through me cost 1. So now, nobody wants this path, right? When you do the extra, you know the shortest path, and you will find out that there is no nobody wants that shortest path. Alright, so they will both exchange messages, control messages, saying that I am blocking this, yeah, I am blocking, and fine, done. Yeah, see, the whole thing is to loop, and so the shortest path with a root will never loop. That's the whole thing about the tree, is that if you have a tree and you have a shortest path, nobody taking longer path, then there is no loop. Alright, so spanning tree is clear. Clearly this has to be understood very, very well, because this is the genesis of many of the things that we will be discussing. And you can see the problems already. One of the problems is if any link breaks, let's say this Ethernet breaks, they will have to do the whole algorithm all over again. And that takes few minutes. And if your stock market, Amazon, Google is down for a minute, you know how many $1 million are going to be lost. Right? And so this is not acceptable. It was acceptable when it was invented back in 1979 and 80, but in 2000 it is not. Alright, so before I go to the next, here's a simple problem. You have to just do this, which thing will be blocked and which will be the root. All right.